How's it going, everyone? You guys hear me, more or less? Cool. Let's talk about things. So hopefully everyone's working on your final projects right now. And we have some things that you should be thinking about in terms of those final projects. So there's going to be this poster session during finals week, June 6th, 4:30 to 6:30 p.m. We're going to be there starting at basically 4 p.m. so you can come in early and start setting things up and whatnot. There will be poster board for posters and easels. There will be like little clippy things, and we'll bring down some glue too so that you can like paste things on if you need to on the poster boards. So the idea is basically we'll all be roaming around and you'll be graded by at least 3 people. So either TAs or me or Ali. We have posted the rubric for final projects on Canvas. Or if we haven't, it will be posted right after class. We have it done. I'm just not sure if Kiana's made it public yet, basically. So you guys can look at the rubric and see it's basically just a bunch of things we'll be rating you 0 through 10 on and then adding them all up. It's computer vision, so oftentimes people can like run things or have cool little demos or something. So if you do, that would be sweet. You get some extra credit points if you have basically some kind of live demo or recorded demo of sort of your project doing something. So that's something to think about. There are 2 options for doing posters. One is basically you make a poster, figure out how to print it, you bring it and put it on the poster board. This can be like printing off sort of 8.5 by 11 sheets of paper and just putting them on individually. If you want to make a big poster, you can make a big poster, figure out a poster printer that you can use, etc. I think there are probably some in the library or something that people can use. I'm not really sure about that. The other option is Kiana has posted a template, and you can basically use her template to do your poster, send it to her, and she will print it as long as you send it to her sort of early enough. So we're asking for those to be sent by Sunday evening, and then she can have Monday and Tuesday to print them, basically. Yeah. Yeah, exactly. Sunday, 3 days before the actual poster session. And that's just because she's probably going to get a bunch of them, and it takes a long time to print posters. So yeah, and lastly, you'll turn in the poster on Canvas, just so we have basically a thing that you have turned in that we can put your grade next to. And so we can refer back to it while we're grading if we need to for any reason. Cool. Anyone have questions about final project stuff, poster stuff, anything? Like not. So last time, Ira came in and gave a super cool talk about face stuff. Do you guys like Ira's talk? People here for Ira's talk? It was pretty fun. That's cool because we talk about sort of a lot of low-level building block type stuff in here. But that talk was pretty application-driven and focused on sort of things that you can do with all these cool computer vision techniques. So it was fun just to like get a little feel for what kind of stuff is out there, what kind of things people are working on. All the AR, VR stuff is really cool. That's something UW has started pushing on a lot. So that was interesting. To remind you guys what we were talking about before Ira's talk on Tuesday, so last Thursday basically, we were talking about semantic segmentation, which is this task of basically for every pixel in an image, we're going to figure out what class that pixel is. So for example, it's labeled all of the, well, let's find my pointer. It's labeled all of the people in red. It's labeled the plants in green. It's labeled all of the traffic signs in yellow, et cetera. So for every pixel in an image, we're just going to figure out what the class of that pixel is. And that's sort of semantic segmentation, just doing that assignment. And we talked about basically this difference between convolution and deconvolution operators, where deconvolution is just sort of doing convolution backwards. So remember, for convolution, you have some input. You're going to take a weighted sum over some area in the input to produce your output. And for deconvolution, you have some input. And to produce your output, you're going to sort of project backwards. So you're going to multiply this input by some weight and add it into this output feature map. And so convolutions we can use for processing images. Deconvolutions operate very similarly. They actually are sort of roughly equivalent to each other if you think about weird things in terms of striding and stuff. And so we talked about basically how we use these convolution and deconvolution operators. For doing semantic segmentation, we have basically an encoder network. And in this case, this is VGG16, which is sort of a classic neural network for doing image classification. But we have this encoder network, and it's going to produce some features. And then we're going to use a decoder network to basically take those features and blow them back up into sort of the size of our original image. So we have this pixel level labeling at the end. And we talked about this problem where basically we have these coarse features that get output from this convolutional neural network. But we want to make these really fine-grained predictions over here. So this deconvolutional network, this decoder, has this really hard job of trying to turn these coarse features that contain a lot of semantic information, these coarse features that say things like there's a dog in the image or a person in the image, et cetera. But trying to take those coarse features and turn those into these pixel-level predictions is difficult. So people have come up with different ways of getting fine-grained information sort of over to the decoder network, basically using some of these shortcut connections. So in this case, this would be our encoder network that takes our image and produces some feature map. Our decoder network takes this feature map and produces our predictions. But we're going to add in some of these connections across so that basically we take fine-grained information from the encoder network, but also this really semantically meaningful feature map that the encoder outputs. When we're finally making our prediction, we're basically incorporating both of these sources of data. So fine-grained predictions or fine-grained feature information, and also this really semantically meaningful but coarse feature predictions that occur later on in the encoder. We also talked about spatial pyramid pooling, which was this idea that objects occur over multiple different scales, and if we're producing sort of segmentation masks for an image, we might want to look at different scales in the input image or different scales in the feature map. So what we're going to do basically is we have some output feature map from our encoder. We're going to do a bunch of different pooling operations of different sizes. So we're going to do a 2x2 max pooling, a 4x4 max pooling, an 8x8 max pooling, et cetera, to get basically a feature map that represents this feature map, but pooled over a few different scales. And that way we have a network that's sort of looking both at coarse and fine-grained information when we go from this output feature map to actually make our predictions. And lastly, we can sort of add in some of these horizontal connections again to get some of this fine-grained information so that we both have sort of this multi-scale aspect from spatial pyramid pooling and these lateral connections that give us fine-grained feature information so we can make really fine-grained predictions for semantic segmentation. We also talked about, for spatial pyramid pooling, we don't necessarily have to do actual pooling operations like max pool or average pool. We could also think about just doing different styles of convolutions. So we talked about A-truss convolutions, where we're going to space out the input instead of sort of making all of the input pixels be next to each other. And it's pretty easy to see, here's an A-truss convolution where the pixels are spaced out one more than sort of our normal convolution. And it's easy to see why sort of using this convolution would result in basically looking at a wider amount of or a larger amount of the input image when you produce the output image. So this is the equivalent of basically doing a larger size max pool versus a smaller size max pool. And then we can do this spatial pyramid pooling with just different sized A-truss convolutions. Any random questions about sort of semantic segmentation stuff? Generally kind of understand what's going on. So we talked about this thing where when we run semantic segmentation, we get these pixel level labels, but they're just for categories. So we have all these people, and they all have the same label. And we don't necessarily know which pixels are actually associated with which person. So that's when we introduce the topic of object detection, which is the task of just taking an image and putting bounding boxes around all of the objects and saying what those objects are. So put a box around this car and say this is a car, put a box around this person, say it's a person, et cetera. So now we actually have this notion of instances where we're not just caring about what class is an object. We actually want to know that this person is distinct from this person, is distinct from that person, et cetera. And we talked about Pascal VOC, which is one of the big detection data sets. It's got 20 classes, 11,000 images, and a little bit more than 2 objects per image on average. Pascal VOC is also labeled for semantic segmentation, so there are pixel level labels as well, and that's actually what the models that we were just talking about are also trained on. They're trained on Pascal VOC semantic labels when we were talking about semantic segmentation. But in terms of detection, we also talked about basically how we're going to evaluate different models, how we're going to score them. And basically, we have this complex scoring algorithm because we are both predicting bounding boxes and also these class probabilities. So first, we have to decide, basically, given a bounding box around an object, is that a good bounding box or not? And what we're going to measure are these two things, intersection and union. Intersection is just the intersection of the two bounding boxes. Union is just the union, normal set theory stuff. We're going to take this division, intersection divided by union, and check to see if that number is larger than a certain amount. So the threshold used for Pascal VOC is 0.5, which means that if we draw a bounding box around an object and that bounding box intersects the ground truth bounding box with an IOU of 0.5 or higher, we consider that to be sort of a correct bounding box for that object. We also have to figure out, basically, if we've correctly predicted the object class or not. So what we're going to do is vary the threshold for how confident you have to be in a certain class to actually assign that class to that bounding box. And then we're going to look at basically the recall and precision at a bunch of different thresholds, take the average as we vary this threshold over time. And you can see sort of as you vary this threshold, you go from really high precision but low recall to basically really high recall but low precision. If we look at the area underneath that curve, that's going to be basically what we term the average precision for a particular class. So this is a measurement just for one class. And then we have 20 classes in Pascal VOC. So we're going to average our average precision over all of the classes. And we get this metric mean average precision. And this is sort of the detection metric that everyone uses for doing object detection. And then we sort of have some method of comparing basically these detectors against each other. It's sort of a hard metric to really like wrap your head around because it's not like this easy task like classification accuracy or something is really easy to compute. With detection, we have like a different number of objects in every image. We have all these different classes, but we also have this bounding box stuff to worry about. So this is kind of an overview of it, but you guys can sort of do some reading on your own too if you're really interested in kind of getting an intuitive idea of why this stuff works. But yeah, we talked about different detection methods. So in the past, we've talked about deformable parts models where we're going to use hog features and sort of slide this filter over the whole image, over the sort of hog features, and look for high responses in that feature map. And we talked about basically we want to use convolutional neural networks to perform detection now because they're so much more powerful for classification. They're probably better for detection too. But if we think about sliding a convolutional network over an image, it would take a really long time because there would be a bunch of different regions that you would sort of be putting through this convolutional neural network all independently. So instead, basically, we're going to do this region proposal thing. And this was introduced by RCNN, where basically we use selective search, which is this method of basically generating successively coarser segmentation masks for an image just based on sort of pixel value. So this looks at what pixels are sort of nearby in color to each other. It generates these segmentation masks at different sort of thresholds for how close pixels have to be to sort of be in the same group. You can look at all of these different pixel masks, segmentation masks, and sort of put bounding boxes around all of those regions of pixels, and we end up with basically a bunch of proposals. And so now we've basically, just by looking at kind of pixel level information in this image, we've generated a bunch of bounding boxes that may or may not encompass objects in this image. They're just sort of like a few random proposals. So instead of doing sliding window over the entire image and looking at basically every possible bounding box, now we have this subset of bounding boxes that actually, we have this prior information that they probably contain some objects or they might be sort of good bounding boxes to look at. And so after we've extracted these region proposals, we're going to run these regions. We're going to resize them basically and run them through this convolutional network, and then run a linear classifier at the end to classify these regions into what category they are for Pascal VOC, or potentially their background, and then all of the category predictions would be 0. We're also going to add on. some extra stuff here. We're going to add on a little bit of bounding box regression. So these region proposals already have basically like coordinates to them, but our proposal process for doing these may have some noise in it. For example, it might contain some pixels that don't actually correspond to, like these two sheep, say, are overlapping. And so maybe some pixels in this sheep were added to a segmentation mask for that sheep. There was this large bounding box that maybe was too large for how big it was supposed to be. So we're going to do this extra step of doing some bounding box regression. So we basically look at the original bounding box, and we can predict basically offsets to that original bounding box in terms of changes in the x and y coordinates and changes in the width and height. So that will just be sort of an extra prediction that we stick onto here. We have all of these linear classifications happening. We'll have another linear model basically that's predicting how much we should change the x and y coordinates and the width and height for a bounding box that we're predicting. We're also going to do this non-max suppression step because, as we see in sort of our selective search image, we have a lot of bounding boxes that overlap with each other, and we basically only want a single bounding box per object. So non-max suppression helps us, as it has in the past, basically avoid doing these duplicate detections. And finally, people do all sorts of crazy stuff at the end to look at basically what kind of classes co-occur in an image and stuff and try to do some extra processing to increase their score a little bit. So RCNN works a lot better than sort of previous methods. So deformable parts models were at about 33% mean average precision. And with RCNN and VGG16, we've basically doubled that mean average precision on Pascal VOC up to like 62.4. So that's really cool. We also talked about how this process is really slow because we're basically extracting 2,000 different images from a single image and running them through this neural network, and that takes a really long time. Where what we really want is some sort of process where basically we have some input image, we run it through some neural network one time, and get some predictions for what objects exist in that image. And so this is the YOLO object detection algorithm, where basically you start with an image, run it through one neural network, and get all of these output predictions. This is it sort of running in practice. So it's sort of robust to handling lots of different objects. It runs super fast, which is cool because we're just now evaluating a single neural network instead of evaluating a bunch of different sort of doing a bunch of passes through a neural network. Kind of stare at it for a little while. So this is all basically, this can run, this is obviously a YouTube video, but this runs in real time if you have a nice GPU in your computer. And if you don't, it takes about 6 seconds to run on CPU. But 6 seconds to run on CPU is still a lot faster than the 20 seconds that it took RCNN to run on GPU. Some interesting driving happening. And you can see sort of the diversity of objects. So there's cars and buses and people and dogs and stuff. That sort of quit out of the whole thing. Cool. So we're going to cover a little bit more on object detection, sort of tell you about modern advances in the field of detection, and also cover some instance segmentation stuff as well a little bit later. Any questions about stuff that we did last time? So for object detection, remember that we're sort of caring about this, this metric of mean average precision. One thing that basically was overlooked kind of originally when people were working on object detection was how fast this stuff actually runs. For deformable parts models and for RCNN, basically at test time, these methods were really slow. And the cool thing about YOLO is that it's a lot faster. So it actually has a little bit of drop in terms of mean average precision from RCNN, but we have this huge boost in terms of how fast it runs, how fast it processes a single image on GPU. So how does this actually work? Remember we originally talked about with object detection, we have this problem where we have this variable sized output. So remember when we're doing classification, we know we're always going to predict basically this 1,000-dimensional vector. We have this network structure sort of built out, and we run an image through our network. We get some output, and we can sort of backpropagate our loss through the network. And neural networks have sort of a very fixed size when you're running them, because they have all of these weights that sort of connect different layers to each other, and you can't really change sort of the size of the output when you're running them, because you would have to add in basically some new weights, and where would those weights come from? How would you kind of figure that out? It'd be weird. So we have this problem where basically we have a variable-sized output for object detection, because there could be one box in an image, or there could be like 50 boxes in an image. And we have to figure out how to map sort of this variable size problem onto this fixed size output so that it's something that we can sort of predict with one pass through a neural network. So if we have an image that sort of looks like this, what we're going to do kind of conceptually is split it into some kind of grid. And in this grid, we're going to basically make a bunch of predictions at each spatial location. So at some spatial location, we're going to basically predict the probability that there's an object that that spatial location should predict. So this is just like probability that basically this bounding box sort of, or this grid cell, this box, kind of contains an object, or there's an object centered in that bounding box, is one way to think about it. And each of these grid cells are also going to produce basically a bounding box that should encompass an object if there is an object sort of nearby, or if there is an object centered in that bounding box. And so what we end up doing is basically predicting a bunch of bounding boxes at all of these different locations. And we also end up predicting basically confidences or objectness predictions for each of those bounding boxes. So if we sort of weight those bounding boxes by how likely it thinks that there's an object in that bounding box, we get basically a bunch of bounding boxes in kind of background regions that have really low confidence. And we have a few basically bounding boxes around the actual objects that have higher objectness confidence.
So once you first
We'll talk about it in a second. This is just conceptually, think about these are the predictions that we want to make. The last thing we want to do is actually sort of figure out what the class probabilities are for each of these bounding boxes. So what we're going to predict is basically something that you can kind of think of as like a segmentation mask over the image. But what this prediction is going to be is basically if this grid cell is predicting a bounding box, and if there is an object in that bounding box, what is the class of that object? So it's basically this conditional probability of, what's the probability of car given object? What's the probability of bicycle given object? Dog given object, et cetera. So our final predictions are going to look something like this, where, again, we have a bunch of background predictions. We have some actual objects that we're predicting, and sort of weighted by how likely the different classes are, and weighted by how confident our prediction is that there is even an object in that category, or in that location at all. And so, for example, we see a lot of bounding boxes over here that are green. It's basically saying, these are probably dog bounding boxes, but they're really low confidence in terms of their objectness prediction because they don't encompass the entire dog in this image. Whereas the bounding box that actually is associated with the entire dog has a lot higher confidence for whether or not it thinks that there's an object in that location. And our final step is going to be sort of the standard thresholding by a certain confidence value and performing non-max suppression to avoid sort of these duplicate detections. So if we think about this setup for object detection, we can basically encode all of this information in this tensor. And this tensor will have some sort of spatial information. So it'll, in this case, it's like 7 by 7, and this is what it was in the original YOLO paper. It's since changed a bunch. But we can imagine this as being sort of an n by n tensor that encodes all of the information that we want for object detection. So sort of the first channel will be just our confidence or our objectness predictions. How likely is this cell to contain an object, or to sort of be predicting a bounding box for an object? The next channels that we have in this tensor are just going to be our bounding box coordinate prediction. So it's going to be our standard x, y coordinates and width and height. And originally, we kind of predicted these directly. We would actually sort of predict, what's the x coordinate, what's the y coordinate, what's the width of the bounding box, and what's the height of the bounding box. Nowadays, we predict offsets from some predefined boxes, and we'll talk about that a little bit later. But basically, these coordinates are just going to contain some kind of information to make the prediction for what the bounding box is at that location. And finally, we're going to have a bunch of predictions for our class probabilities. And again, as we talked about, these are sort of these conditional probabilities of if there is any object here, what object is it? So we have basically each of the classes: cat, bird, dog, television, person, car, etc. So for Pascal VOC, this would be 20. There are other data sets where you might have more or fewer objects in that you're sort of predicting for or looking for. And we could imagine this as basically predicting sort of one set of bounding boxes over an image. And in practice, we could actually stack multiple of these if, at some particular location, we didn't want to just predict one bounding box, maybe we wanted to predict a few bounding boxes. And this is useful because oftentimes there are, a wide variety of different sized objects in an image. And if you try to make basically your bounding box predictor span that wide variety of different objects that it could potentially predict, it'll be this really hard problem where basically, this sort of vector right here at the bottom right corner of the image could be responsible for predicting basically a really small object in the bottom right corner of the image or a really large object in the bottom right corner of the image. And it would just sort of, and all of those predictions would have to sort of come from this same prediction mechanism or sort of these same neurons in your network. So if we stack basically this tensor multiple times, we can, at every grid location, predict multiple bounding boxes, predict multiple class probabilities for each of those bounding boxes, and confidences associated with each of those bounding boxes. So what we are going to end up doing is predicting some number of bounding boxes. So this figure is from YOLO version 2, which predicts 5 bounding boxes for every spatial location. And those bounding boxes are distributed over a bunch of different sizes, basically. So we have, a really small bounding box, a slightly larger bounding box, a couple of sort of medium-sized bounding boxes that are of different aspect ratios, and then one large bounding box that would sort of go for really large objects in the image or sort of objects that take up the entire image. And we sort of want this spatial diversity between boxes. We want to predict some small boxes, some medium boxes, some large boxes, because they're objects of different size in an image. And what we're going to do is basically, instead of predicting these coordinates directly, we're going to use these bounding boxes as priors, as sort of bounding boxes that we know may be close to sort of the size of what the actual object is in the image. And we're going to take these priors and just predict offsets from those priors, just like we talked about with bounding box regression in RCNN. So instead of predicting just x and y coordinates from scratch, we're going to predict some kind of offsets. And importantly, these priors should sort of make sense for what the data is that you're looking at. If you don't have any really small objects in your data set, it doesn't really make sense to have any bounding box predictors that are trying to find really small objects. Same thing if you never really have any really large objects, it doesn't make sense to be looking for really large objects because these large priors will basically never be used. So what we do is use k-means clustering on the training data. We look at the bounding box width and height and cluster it into, in this case, 5 different clusters, but you can imagine a range of different k's that you can use. And from that, we can basically recover what are sort of the general sizes of objects that we would expect to see in our data set. And we can use those as priors for bounding box sizes that we might predict. So now we talked about basically how we're going to predict these offsets. How does this actually work? So imagine that sort of you're looking at a particular cell. So in this case, we're going to predict a bounding box from this spatial location, or sort of this pixel in the feature map. So this cell is going to have some offset from sort of the top left corner of the image. And we're going to say that that offset is Cx and Cy. And we're going to predict offsets from sort of our prior bounding box that we talked about. And our prior bounding box will have width and height, Pw and Ph. So what we end up predicting are these t values, Tx, Ty, Tw, and Th. And we use those values to compute basically the actual bounding box. And the actual bounding box is associated with basically the distance from the top left pixel, or sort of the top left location of this grid cell. So we're predicting Tx and Ty, and we're just going to take the logistic activation of Tx and the logistic activation of Ty, so that each of those fall within 0 and 1. So if the logistic activation of Tx, for example, were 0, we would be sort of along this area, along the y-axis. If the logistic activation of Tx were 1, we would be over in this region. Same thing with Ty. If it were 0, we would be here. If it were 1, we would be here. Taking the logistic activation just kind of constrains the center of this bounding box to fall somewhere within this grid cell. So we make these predictions for Tx and Ty, and then when we want to calculate the center of the bounding box, Bx and By, we just take the logistic activation of Tx and add it on to however offset we were sort of originally, this value for Cx. And similarly with By, if we want to calculate basically the center of the bounding box, we take the logistic activation of our prediction Ty and add it on to sort of the offset of this bounding box from the top left corner of the whole image. And that gives us the center of this bounding box. And we're going to do kind of a similar thing for the width and height. We're going to basically predict this offset, Th and Tw. But we're going to basically take, so take an exponential function of T width and Th. So our actual bounding box width is going to be sort of our prior for what the width might be times e to the t width, and our bounding box height is going to be the prior for the bounding box height times e to the t height, or th. So in this case, we have this kind of weird encoding, but if you actually sort of work through some of the math here, some of these things make sense in terms of why you would want to predict basically this t width and t height value that you're doing this exponential function on, because you want to scale basically this prior bounding box by some amount. So you may want to double it in size, or you may want to cut the size in half. If you just kind of try to predict those numbers directly, you have sort of this weird prediction where you're kind of unbounded in one direction, where you could predict anywhere. If you want to make the bounding box bigger, you're predicting some number from 1 to kind of infinity. And if you want to make the bounding box smaller, you're predicting some number from 1 to sort of 0. So that's a harder prediction to make. If you want to double the size, you'd have to predict 2. But if you want to cut the size in half, you'd have to predict 0.5. You have this sort of compression that happens when you're kind of trying to scale the bounding box smaller. And if you use this exponential function instead, your predictions that you're actually making are a lot easier to deal with, because if you basically predict any number that's larger than 0, you're going to make the bounding box larger. If you predict some number that's smaller than 0, you're going to make the bounding box smaller. We had some question over here. Okay. And the encoding for shifting basically the center of the bounding box is, I don't know, a little bit strange, but it's sort of nice in practice, because in the end, we basically want to predict a bunch of bounding boxes spaced over the entire image. This constraint basically makes it so that the center of this bounding box, if we're predicting it from this grid cell, has to fall within the region of that grid cell, and that kind of makes sense. It's also nice because all of these functions are pretty easily differentiable. which in practice, since we're doing this neural network stuff, we're going to run it through the neural network, calculate some loss, and then backpropagate that loss through the neural network. So we need all of these functions to be differentiable to do that gradient backpropagation. So on the topic of loss, we basically need some loss function that we're trying to optimize. And in the case of YOLO, we have these 3 different components to our loss function. So we have this confidence prediction that we're making, and we're going to have some kind of loss associated with that. We have this bounding box localization that we're doing, where we have maybe some ground truth bounding box, and we want our prediction to be close to that ground truth bounding box. And we also have some classification loss, where if there is an object, we have to predict a bounding box for it, and we also have to predict what class it is. So we want to basically predict the right thing, and if we're wrong, we incur some loss for that. And we're going to have basically, so the whole loss for basically the entire algorithm is going to be a combination of these 3 losses. And we can use basically some scalar factors to trade off how much we care about each of these individual parts of the loss function. In practice, these alphas are generally set to like 1 or 2. So there's not a whole lot of like trading off between these different factors. But it is something you can think about in terms of how you would change sort of the different pieces of the loss function depending on what the objective might be that you're trying to optimize for. So in terms of this confidence prediction, it's basically this binary prediction that we're doing. It's logistic regression, where we want to basically say either yes or 1 if there is an object that's sort of centered in that grid cell, or 0 or no if there isn't an object in that grid cell. So we're going to use the standard binary cross-entropy loss for that, which you guys have worked with a bunch and we've done a bunch of math with. For this localization prediction, we have this kind of weird encoding that we're talking about, where we're predicting these tx, ty, tw, and ths. But if we have some ground truth bounding box in this image around some object that we actually care about, it's pretty easy to sort of figure out what prior box, which one of sort of these boxes, is closest to the ground truth bounding box. And then we want that prior box to sort of predict the actual ground truth bounding box. And it's pretty easy to take that prior and run these calculations backward to figure out what the actual prediction should be. And then we're just going to do regression to predict what sort of what the ground truth values are, or what we want our predictions to be. And so the loss that we're going to use for localization is just mean squared error or root mean squared error or whatever, to basically accomplish this task by regressing to what the coordinates of the bounding box should be, or what the predictions for the bounding boxes should be in terms of whatever the representation is that we decided to use for our bounding boxes. And finally, we have this classification problem, and we can do a few different things here. We've talked about in the past doing softmax classification, and that's one option. We can basically do multi-class cross-entropy, which we've talked about. We can also frame basically each class prediction as being just a binary decision, or as being sort of a logistic regression problem. And then it's just kind of this one versus all situation where you say, is there a cat or is there not a cat? And independently, is there a dog or is there not a dog? And in practice, sort of using either of these 2 setups, either doing the softmax operation or just using logistic activations and doing this one versus all thing, work basically about the same in terms of accuracy and stuff. And in practice, the logistic activation and kind of framing this as a logistic regression problem is a little bit nicer, because a lot of times in these detection data sets, not necessarily in Pascal VOC, but in other detection data sets, we have overlap between different classes, where a bounding box or sort of an object might be, it might be like an animal and also a mammal and also a dog or something, where we have a bunch of different labels for one particular bounding box, and we don't want to necessarily enforce this softmax assumption that each of the labels are distinct or mutually exclusive from each other. So Does everyone sort of understand loss functions? People have questions? Yeah. Yeah, we've done a bunch of little tuning for how much of these things actually matter or what sort of the trade-off should be. And in practice, it doesn't have like a huge effect, but it does have some. We're probably in some kind of local optima, but I'm sure you could do some fine-tuning to find something a little bit better. Yeah, so I mean, we have this encoding for all of the things that we care about in object detection. And basically, we're just going to run a neural network like we had in kind of the original slide, if you remember. We sort of have this neural network, and what we wanted is just all of the predictions for that image. And what we're going to do is just run a neural network and try to get it to predict this tensor. So we input an image, and the output is some tensor that looks like this. And during training, we sort of try to make our predicted tensor look a little bit more like kind of the ground truth tensor encoding of that image. But in practice, we don't necessarily know like which parts of the network, since the entire network is kind of getting fed in to predict this tensor, we don't necessarily know like which parts of the network are responsible for predicting the class probabilities versus which parts are predicting the bounding box or which parts are predicting this objectness score. It's just sort of this one big unified system. And this means that we can't necessarily tune each component individually, but it's also nice because we can just do gradient backpropagation and do gradient descent. And this whole network will kind of train. And the theory goes that backpropagation or gradient descent is good at optimizing some loss function. So as long as your loss function is pretty close to what you want, the network will kind of fix itself and kind of proportion out capacity and stuff to minimize your loss function sort of as well as it can. So we're not necessarily saying, or like the loss functions don't necessarily control like, this part of the network should update in this way. The network and gradient descent just kind of take care of that on its own. Yeah. What do you mean? Yeah, or so we have these sort of 5. So instead of basically, so all we're going to do is instead of predicting sort of x, y, width, and height components sort of from scratch, we have these prior boxes that we're going to use, and we're going to predict offsets from them. So initially, basically, if you didn't predict sort of any component for tx, ty, t height, or t width, the bounding box would just be centered in, I mean, you can assume basically that you're predicting 0 for all of these things. Then the bounding box would be centered in the middle of the grid cell that's doing that prediction, and it would have kind of its original width and height. And what we're doing is predicting offsets from that. So either shifting it to the left or up or down or right, making it a little bit wider or a little bit smaller, et cetera. So the location. I mean, we're doing it at every location, right? So at each of these locations, we're going to predict bounding boxes. So this grid cell might predict this bounding box, but it might also predict a bunch of other bounding boxes, depending on how big we make this tensor. So in this case, we're just predicting basically one bounding box per location, but you could imagine increasing that to sort of 5, and then it might add in some other bounding box predictions. And they would all be basically centered somewhere within this cell, but just sort of somewhere in that area, basically. Yeah. So if you go back to the they may not necessarily. It depends on what you're doing. If you use like a softmax over sort of each of these vectors, they will add up to 1. If you're doing this kind of one versus all logistic activation, then they may or may not. Yeah, so none of the above is basically handled by this objectness prediction. So remember that these are basically this conditional probability where we're predicting like what is the probability of cat given that there's an object in this cell, but there may not be an object there. So if we actually want to predict, like whether or not this bounding box is a car, we're going to take the objectness prediction, which is the probability there's an object, and multiply it by this conditional class probability, which is the probability of car given object, to recover basically the full prediction. And this allows us to do some sort of nice things, basically, by kind of decomposing it into these two different components. And the big thing is basically there aren't, as we talked about before, basically we have this problem where there aren't a lot of objects in every image. So we have this huge imbalance of positives and negatives. And we have this situation where if you just like have unconditional probabilities here, if you just do probability of cat, probability of bird, probability of whatever, and no objectness prediction, then almost all the time there's not going to be a cat in a particular cell, or there's not going to be a dog or whatever. So those probabilities are going to end up, your neural network is going to fall into this local minima of always predicting 0 for all of those classes. Or it's really hard to get it to not do that. And so we talked about with deformable parts models, what they did. They had the same kind of problem. And what they ended up doing was this hard negative mining, where you want to kind of balance out the number of negatives and positives that you're feeding into your system. This is sort of doing a similar thing. Doing this decomposition means that we have this one prediction, which is just whether or not there's any object. And if we assume that there are usually 2 or 3 objects in an image, then this is just 7 by 7, which means that 1/25 of the time or 1/20th of the time or something, there's going to be an object in a particular grid cell, which makes this not necessarily sort of go to 0 immediately or just kind of stay at 0. So we actually end up learning something in terms of predicting the probability of just any object in a grid cell. And then each of these conditional probabilities only come into play if there is an actual object there. So if there isn't an object in a grid cell, we don't care what these class probabilities are, because these are conditional class probabilities conditioned on the fact that there is an object. So we can just ignore them in our loss function. But if there is an actual object, then we can look at what those class predictions are and calculate some loss, figure out the gradient of that loss, do the backpropagation step, et cetera. This kind of worked here for detection. It could work if you were doing some other kind of task where you had this same thing. Basically we have just like a hierarchy. And the hierarchy is pretty flat, but it's like object or not, and then underneath object is all of these different classes. But you can imagine if you had some other kind of hierarchy that you were trying to predict, and each of these individual things were sort of rare, this decomposition might be something that you'd be interested in, of first predict whether or not sort of the root node exists, and then you can predict kind of the subnodes based on whether or not the root node is in play or not. So potentially. Oh yeah, so this is kind of the loss function, and we're going to do basically our standard gradient descent, where we push an image through the network. We have some output tensor. We have the ground truth tensor that we actually kind of care about, and we basically try to modify our output to look a little bit more like the ground truth that we're going for. We calculate our gradients, and we backpropagate that through the network, and just kind of magically the neural network learns to do this task just by sort of designing the output and coming up with this parameterization for detection as this tensor that we can predict with a neural network. Did you have a question?
Yeah.
Yeah.
Do you find that really
Yeah, it can be a little bit in practice. It doesn't usually matter that much. Mostly because this feature map that we're going to be using is generally pretty fine-grained with respect to how large the objects are. And going from basically like getting a sigmoid to predict 0.95 is pretty easy. Getting to predict 1 is impossible. But the difference between predicting 0.95 and predicting 1 is very little in terms of how much it's going to shift this bounding box around. So that distinction doesn't end up actually mattering a whole lot. You can use sort of linear activations instead. It's just a little bit less constrained. So you end up having a little bit more model instability, and it, in general, performs a little bit worse. But it's not like a huge deal either way, basically. Question? No, not necessarily. So you can imagine if there's a really small object, it might be, it'll be centered somewhere within this grid cell, but it could be just like a really small portion of this grid cell or of sort of this cell in the feature map. So it just kind of depends. Cool. So the original version of YOLO was at about 63 mean average precision. We made a bunch of updates over time and sort of pushed that higher and higher. But in the meantime, obviously, other people were also working on kind of their own systems. So there were updates to RCNN in terms of fast RCNN, faster RCNN, using ResNet to form sort of the backbone for faster RCNN, this fully convolutional network stuff, all sorts of things that people were working on. So nowadays, we've basically gotten much higher accuracies or much higher mean average precision on Pascal VOC. But I'm going to take you basically also sort of through the RCNN approaches because they are kind of the main approach that people take to object detection these days. And it's important to kind of understand what's going on from kind of the original RCNN paper. So remember that sort of the task that we were trying to solve and kind of this big problem is that RCNN is slow. You have your image. You're going to extract a bunch of these regions of interest, a bunch of these bounding box proposals, basically, from selective search or from some other method. And then we're going to take these regions, resize them to some standard size, and run them through our convolutional network. With this convolutional network, we're basically going to be predicting class probabilities using some SVM. We're also going to be doing this bounding box regression step, or predicting sort of these offsets from this bounding box. But since we're running this convolutional net a bunch of times, it takes a really long time to process a single image. So what fast RCNN did was said, instead of running this convolutional net a bunch of times, let's run one convnet to extract some features, and then figure out how we can pool sort of different regions of this feature map and make predictions basically off of different regions in the feature map instead of different regions in the image. So we still have this scenario where we have this input image. We're going to run selective search over this to get some regions of input, or some regions of interest from our sort of region proposal method. And then we just run a single convnet, so like VGG16 or some other thing like ResNet or something, over this image, and we produce some output feature map. And now we can basically take these regions and map them onto this feature map. And now instead of basically resizing the input image to, or sort of, when we had this step here, we were extracting these regions, resizing them and running through the convnet. Instead, we're going to resize basically the regions of the feature map, so they're all some standard size. And then we can run that through some standard, basically fully connected layer, or fully connected layers, and do some final predictions based on that. So we can predict some offsets to our bounding box. We can also predict some kind of class probabilities, et cetera. But the big breakthrough here is, instead of running this convolutional network like 2,000 times for a single image, we just have to run it once for this image, and then we're going to basically extract sort of these regions from this output feature map, and we still have to run these linear classifiers or do this bounding box regression, like 2,000 times for the image. So we're still running basically this subnetwork a bunch of times, but it's much smaller than our original convolutional network was for for processing just a single region. And the key point here is basically this ROI pooling that FastRCNN does, where we basically are mapping our region of interest onto this feature map that we have for the image. And since we have some neural network here, neural networks, as we talked about before, basically take some fixed size input and produce some fixed size output. We have to basically map these regions of interest to some fixed size so that we can run them through this sort of subnetwork and predict class probabilities and bounding box information and stuff. And so the way that we're going to do this resizing and kind of make them all be the same size is using this region of interest pooling method. And ROI pooling is one way of doing this, but it's sort of been subsumed in the last year by a different method that's very similar, but just like very similar but kind of related, called ROI align, which you can kind of think of as just an extension of region of interest pooling, basically, and sort of equivalent in terms of computational, in terms of like the amount of computational complexity, the amount of computation needed. So instead of talking about ROI pooling, since it's basically already obsolete, we'll just talk about ROI align, because it's kind of the updated version, or sort of a better method of doing it. So what we're going to do is basically we have some feature map, which is this dotted grid in the background. And we have some region of interest, which is sort of this outer rectangle that lies somewhere in this feature map. And this feature map is generated by selective search, so it's not necessarily kind of like nicely aligned with the pixels in our output feature map. It can just kind of lay anywhere in this feature map. And we want to produce some fixed size output. And in this case, we'll predict basically just a 2x2 little feature map for this region of interest. So what we're going to do is in each of these pixels that we want to produce in sort of the output feature map, we're going to sample sort of a fixed number of points. In this case, we're also going to be predicting or sampling a 2x2 little grid of points. And for each of these points in each of these pixels, we're going to just do bilinear interpolation from the original feature map that we're looking at. So we're going to sort of estimate, what is the value of this pixel in the region of interest? What is the value of this pixel? What's the value of this pixel? What's the value of this pixel? And remember, from bilinear interpolation, this pixel will just depend on sort of the surrounding pixels from our feature map. And this pixel would correspond to sort of these 4 pixels in the input feature map and would be some linear combination of those, et cetera. And once we've calculated basically these 4 components of this part of our region of interest, we're going to do some kind of pooling operation on top of them. That pooling operation could be max pooling or average pooling. It's one of the standard ones that we've already looked at. And we're going to run that for sort of each of the number of grid cells that we've decided to use for this fixed size representation. So you can imagine you can kind of do this with any size or shape region of interest, and anywhere it might kind of occur in this feature map, all we're doing is basically some basic bilinear interpolation and then pooling the results of those operations so that we end up with kind of this fixed size. So even though this region of interest is much taller than it is wide, we're going to end up with this 2x2 representation that encodes a lot of the information that is going on in sort of this region. So it's going to end up encoding, what are the features like that correspond to the pixels that fall within this region in the original image. Do people more or less understand ROI align and how it's sort of taking this variable-sized region in our feature map and just mapping it to this fixed size output, basically? And so this is cool because we basically run our convnet a single time, and we get these regions of interest from something like selective search. We do ROI align or ROI pooling to get this fixed size representation, run them through our fully connected layers, and get some prediction. And it's much faster because the only component of this network that we're running multiple times is this last linear layer. but we still have this really slow region proposal method because selective search, doing sort of this successively coarser-grained segmentation mask over an image, takes a really long time. In practice, it takes about 2 seconds per image. So now kind of the bottleneck to speed in terms of fast RCNN is our region proposal method. And what we really care about is speeding that up. And that's where faster RCNN comes in. So now instead of basically doing selective search, what we're going to do is run our convolutional network over the image. We're going to produce some kind of feature map that we talked about before. And we need some regions so we can do ROI pooling to run through our classifier and stuff. And how we're going to get those regions is just add on another little subnetwork that will do the region proposals for us. So this region proposal network basically takes this feature map and does the same process that we were talking about with YOLO, where at each of these spatial locations, we're going to predict some bounding boxes that may or may not be good bounding boxes for that region. It does the same thing as YOLO because I copied a lot of the work that faster RCNN does when basically designing YOLO in terms of how we predict these bounding boxes and stuff. So we have basically our convolutional network that outputs some feature map. We're going to process this feature map to produce a bunch of bounding box proposals. And then we're going to do region of interest pooling on this feature map to basically extract some fixed size representation of each of those bounding boxes. And we're going to run that through our classifier and our bounding box regression and all of the things that we had before. So we have sort of this additional region proposal network. So it adds a little bit in terms of computation time. But we're getting rid of selective search, which took 2 seconds per image before. So now we have what is more or less a single neural network that can do the same thing. We have like a single neural network that can take an image and output more or less all of the components of detection. We still have to do sort of this piecewise ROI pooling and run them through this subnetwork each independently. So it still takes a little bit more time than kind of these methods that will take an image and just produce all of the detections at once. But it's a lot faster in practice than the original RCNN method. So detection is pretty cool. And we have this data set, Pascal VOC. And remember, we started out with deformable parts models at 0.33 mean average precision, or 33% mean average precision. Nowadays, we're like almost at 90% mean average precision. So this is class-wise average precision, and this is the mean average precision. And we see we have some faster RCNN stuff up here. We have some different training data that people are using. But basically, we started to saturate Pascal VOC in terms of how good our predictions are on this data set. So anytime you basically have reached the limits of one data set, you basically make a new data set that's bigger and harder. And that's where COCO comes in. COCO is the Common Objects in Context data set. And it is significantly larger than Pascal VOC. So Pascal VOC has 20 objects. COCO has 80. It has about 100,000 training images instead of around 10,000. Or I think VOC has like 20 or 30,000 training images. And it has a lot more object instances. So this is interesting because remember that Pascal VOC has somewhere between 2 to 3 on average instances per image, whereas COCO has like 8 or 9 objects on average per image. There are a lot more objects in each image. And there are also, when you look at sort of the statistics or metrics of these images, there are a lot smaller objects in these images. So we have over here like a bunch of different people that are sort of each labeled. And to go along with COCO, it sort of introduced this new detection metric. So remember that before we were looking at mean average precision with an IOU threshold of 0.5. Now we're going to use mean average precision, but averaged over a bunch of different IOU thresholds. We're going to use basically all of the thresholds between 0.5 and 0.95 with a step every 0.05 in terms of IOU. So we're not just kind of concentrating on mean average precision at this IOU threshold of 0.5. Instead, we're averaging over these larger IOU thresholds. And you can think about like an IOU threshold of 0.95 means that your predicted bounding box and the correct bounding box have to be almost perfectly aligned with each other. To basically get an IOU of 0.95, you have to have only like maybe like a 1 or 2 pixel error in terms of like width, height, and x and y coordinate. So what this metric ends up doing is basically putting a lot more weight behind how well your bounding boxes actually align with the ground truth objects, and sort of minimizing a little bit how much the actual classification matters, because what matters a lot more is how good your bounding box predictions are. We also have, in this data set, instead of just bounding boxes for each of these objects, we actually have these segmentation masks for each of the objects in the image. So instead of just sort of a box over this person playing tennis, we actually have this segmentation mask where we have someone has gone through and basically drawn an outline around the person, and all of the pixels inside that outline correspond to that person. And it's pretty easy to take a segmentation mask like this and produce a bounding box. You just look at what's the sort of extrema in terms of x, y, and sort of the minimum x, the maximum x, minimum y, and maximum y coordinates. And you can produce a bounding box that encompasses that segmentation mask. But it gives you a little bit more options in terms of kind of pre-processing and stuff that you can do to this data. This data set was originally produced by Microsoft, but they were scared of liability issues or something, so they made it its own little nonprofit or something. So the paper is Microsoft Cocoa dataset or something, but now it's just cocodataset.org. But it's a really cool data set. And we can basically run all of these same methods that we were talking about before on the Cocoa dataset, and we see that instead of basically being up in the high 80s, we have a lot farther to kind of go in terms of our metrics on Cocoa. So this is YOLO v3, kind of the most recent version of YOLO. RetinaNet is basically faster RCNN, but with a little bit of change to the loss function. They use this new thing called focal loss, which, if you guys are interested, you can look up, basically. But we have a bunch of different detection metrics, or detection methods here, sort of ranked by both Cocoa average precision and also inference time, so how long it takes them to process an image. And in general, we kind of get this nice curve, or sort of this trade-off, where you can see if you want your detection method to be really accurate, and you're OK with spending a little bit more time on it, you can be sort of somewhere up in this region. And if you want your detection method to be fast, you can sacrifice basically a little bit in terms of how accurate your method is and get something that's a little bit faster. So in general, this is just, it's cool that we have this trade-off, but also we're, stuck in the 30s or low 40s in terms of average or mean average precision on Cocoa, which is a cool place to be because basically it means there's a lot of improvements that we can make and a lot of work left to do in object detection. So even though some of these things look like we're getting really good results, basically there's still a lot of space left open in terms of making these detectors work better, which is nice. So we talked about segmentation, like semantic segmentation, where we have these pixel level labels, and we're just labeling every pixel with what class it belongs to. We also talked about detection, where we're producing bounding boxes, and we're predicting both category, but also on an instance level, we have sort of distinctions between what is this car versus what is this car. We don't lump all of the cars together in one large bounding box and call it a day. We're actually predicting separate bounding boxes for each car. So we have instance level information over here, but we have this pixel level kind of labels over here. And one question you might be asking is why don't we do kind of both of these things at the same time? So why don't we predict, why don't we do these predictions on a pixel level, but also have differences between different instances in this image? And this task is called instance segmentation. So given an image, we actually want to produce instance level segmentations where we know what class every pixel belongs to, but also which instance it belongs to. So for example, we have a person here, and we have the sort of outline of the person. So we know that all of the pixels in this outline correspond to the person class. But we also know that all of these pixels for this person are a different person than sort of all of these pixels that correspond to some other person. And they're all different than sort of these pixels that correspond to this car, et cetera. So instance segmentation is this new task that's sort of just come about because when we're talking about the COCO data set, we actually now have the labels to do this task. So now we actually have basically a data set labeled with all of the instances have these separate segmentation masks. And the idea is, why don't we start trying to train neural networks to do this task? So kind of the state of the art in instance segmentation right now is this technique called mask RCNN, which takes RCNN, which is this detection framework, and basically adds on this mask prediction function. And we'll zoom forward a little bit because it's kind of boring for a while. But we see that basically at every frame we're kind of predicting both sort of these masks and category level predictions, and also this instance level prediction where that person is distinct from that other person, et cetera. We have this weird flashing effect that kind of happens just in this demo because there's no kind of temporal information that the model is incorporating. So every frame, it's just doing this processing from scratch, and it's not necessarily going to keep the same instance label from one frame to the next frame. But the important part is that all of the instances are sort of distinct. I like that it sort of saw that there was a person in that bus window. Let's see if we can go back to that. See if there even is a person in that bus window. Yeah. That's pretty cool. So we can see that this is, in some sense, sort of a generalization of object detection, where object detection, we're producing these boxes, and with instance segmentation, we're actually producing this finer grained labeling. We're actually looking at what these masks are. I don't know how to get out of this. There we go. OK, so mask RCNN is basically very similar to RCNN, but we're going to predict this mask instead of the bounding box. So we're still having this whole network that basically does the region proposal stuff and predicts this feature map. We're still going to do region of interest align. And this is actually where ROI align came from, was this mask RCNN paper. So we take some region of interest in our feature map. We produced some fixed size map. And then we're going to run this through some convolutional layers and basically produce a segmentation mask for that particular region in the image. And we're also going to have some sort of classification that gets predicted as well. We want to predict basically, is this a person or a dog or a cat or whatever. And what this actually ends up looking like is we basically just take faster RCNN. So we have sort of our typical faster RCNN that we just sort of covered, where we have an image, it goes through a CNN, it produces some region proposals, we perform ROI align and run them through here, and we get class predictions and bounding box predictions. And then we're just going to add on this extra sort of little subnetwork that also predicts masks on top of doing sort of this full detection prediction that we had with faster RCNN. So we basically, all we've done is taken faster RCNN and add on these extra predictions that predict these segmentation masks. But as you guys sort of can tell, it works super well in terms of doing these instance level segmentations. And in practice, this is kind of an approach that most people who are working on instance segmentation, this is kind of, as far as I know, this is sort of the current best in terms of doing instance segmentation, but a lot of the approaches look very similar, where basically we're going to kind of run detection on the image first, sort of produce a bunch of bounding boxes for the image, and then we're going to look inside each of those bounding boxes and produce some kind of segmentation mask. So mask RCNN is one way of basically producing all these bounding boxes and then looking at those bounding boxes and producing some kind of segmentation mask for that bounding box. Mask RCNN actually works super well on COCO, both in terms of when you evaluate the segmentation masks, but also it's just adding on this extra component to faster RCNN. So you can also just measure the detection performance in terms of the bounding boxes and stuff that it produces. So when you add on sort of all the bells and whistles and use like the most powerful network that they use in their paper. It gets 41 mean average precision on COCO, but it takes, I think, somewhere around 500 milliseconds or something on sort of the GPU that I was using to create this plot in general. So somewhere around 2 frames per second. So it's pretty high up in terms of mean average precision, but it would be like way over to the right in terms of how long it takes to run this method at inference time. So when we're talking about sort of this Pareto optimal curve of trading off accuracy and time, mask RCNN is way over on the side in terms of being very accurate, but taking a lot longer to run sort of on an image. So this is another sort of cool little demo of running a bunch of different techniques on the same video at the same time. So in the bottom right, we have our semantic segmentation that we talked about originally, the Deep Lab paper that we were discussing. We also have 2 versions of YOLO just doing detection at the top and mask RCNN in the bottom left. And if you kind of stare at this and kind of watch it for a while, you can see some of the differences between the different methods, pick up on some sort of subtleties in terms of like what's predicting what different things. But it's just kind of interesting to look at sort of the differences between the semantic segmentation predictions versus the mask RCNN predictions versus the detector predictions at the top. So one thing that I've kind of noticed is like the mask RCNN predictions, it's using this pretty coarse prediction mechanism. So in general, I think the deep lab predictions for semantic segmentation are a little bit better in terms of predicting really fine-grained stuff. But they're both pretty good. So there's like a little bit of kind of waviness, especially like for the wheels of cars and stuff. Like if you look at kind of the wheels of this car, I don't know how well Deep Lab does it. It's kind of hard for me to see. Yeah, so the predictions for sort of on semantic segmentation for the wheels of these cars are much better than, I don't want to click on that, are sort of much closer aligned with the actual pixel level labels than the mask RCNN predictions. And that's kind of a sort of a fragment of how mask RCNN does its predictions. Since it does this ROI pooling, it's basically trying to predict these masks from like a 7x7 feature map. And obviously a 7x7 feature map is pretty coarse, whereas when we're talking about Deep Lab, we're using this kind of horizontal information that we talked about from the fine-grained features to predict the segmentation mask. So it can use a lot more fine-grained information for predicting these segmentation masks. And the segmentation masks from semantic segmentation end up being a little bit sort of closer in terms of this fine-grained stuff. But again, we don't have sort of instance level labels. All we have are sort of class labels. So one question is like, is there some way to kind of merge the benefits of doing semantic segmentation and having these really fine-grained predictions with the cool stuff that we get with mask RCNN of doing these instance level predictions? I don't have an answer for that or anything, but it's a cool thing to think about if you guys are sort of thinking of doing research in the future. Just to preview a little bit what we're going to be talking about next time, the COCO dataset is also cool because it has captions. And in particular, each image in the COCO dataset has 5 different captions. So they just sent it out on Mechanical Turk, and they said, describe what is going on in this image. So we get things like the man at bat readies to swing at the pitch while the umpire looks on, a large bus sitting next to a very tall building. So we have a huge variety because we have 5 captions per image, and we have a bunch of different images. Some of the captions are like active, like the man is getting ready to swing, and some of them just sort of describe this static scene, like the bus is sitting on the road or whatever. But one thing to think about is basically, we talked about doing semantic segmentation or detection or whatever, and in some sense, like all we're really doing is sort of this pattern matching process where we're like looking at an image and we're looking for a pattern of pixels that looks sort of like a car. We're looking for a pattern of pixels that looks sort of like a dog. And maybe like this kind of simple pattern matching is like an easy task. And maybe what we really want to do is like figure out if we can actually understand the image or understand what's going on in it. And maybe if we want to train some model to actually produce a caption for an image, maybe to produce a caption for an image and to produce sort of a really good caption, you actually have to like understand what's going on in the image at some deeper level. And so that's kind of what motivated this task of automatic caption generation, or sort of caption generation for images. But to do this, we sort of have to model both visual information and language. And so we're extending out from just kind of working on computer vision and starting to connect it to some different fields. And in particular, we're going to start connecting it to natural language processing, where we're actually going to have to look at sort of characters and words and sequences of these things and start to think of basically processing information in the time domain as well as in sort of the spatial domain that we normally think of for images. So next time, we'll start talking about basically using neural networks to do some natural language processing stuff and how that relates to caption generation. But that'll be on Tuesday. So see you guys later.